So, hi everyone. Uh, I think we will start after 2 3 minutes. I'm waiting for others to join, and then we can start. So it's already 3:05. I think we should start. So let me just start with the introduction. So good afternoon, everyone. My name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. So I'm basically the course TA for the NPTEL course CMOS Digital VLSI Design, and the course is taught by Professor Sudev Dasgupta from IIT Roorkee. So far, we have covered four live problem solving sessions. Today is the fifth live problem solving session, and this will also be pertaining to combinational logics, the logical efforts. And this week will mark the end of combinational circuits. From next week, we will take up problems pertaining to sequential circuits. And I think in the last one, we'll maybe discuss the concept of memory and its design also. I'll take problems from that. So today's fifth lecture. After this, there will be three more live problem solving session. This week I'll concentrate mainly on combinational circuits and mostly on the logical effort, finding out the optimal delays, optimal path effort and all, and some problem related to previous week content that we had discussed, because some people wanted to get a hold of that NP logic. So I kept two problems, one problem around that, and one problem I had already prioritized last time, that I'll be discussing some problems pertaining to where we have a stack of CMOS pull down and pull down network having same similarities. Now, coming to the etiquettes of the problem solving session. So, you all of you must be knowing that you should have an authentic username. No fictitious or inappropriate username will be added. Camera and microphone needs to be turned off throughout the session. And if you feel you have to ask some doubts, and now since the role is slightly less, you can always unmute yourself and ask a doubt, but preferably ask doubt after a question is solved. I'll give time to asking your doubt, so unmute yourself and ask your doubts. And if you're comfortable in the chat box, please go ahead in the chat box. And if sometimes you want to raise some query and question, please raise your hand, and your query will be entertained. And session is recorded, and just like every other session, this session's link will be uploaded on the Google Sheet that is already being shared with you, and also the annotated PDF and PowerPoint will be made available. And other things are self-explanatory. So let's start. These are just a couple of questions that are, you can say, one word type answer. So what I would like is you guys should answer these type of questions. So first question is, clock feed through is caused by option A, capacitive coupling between clock input of precharge device and dynamic output node. B, capacitive coupling between power supply and output node. C, capacitive coupling between clock input and power supply. D, capacitive coupling between power supply lines. So you guys tell me, you can write your answer in chat box. Just write down the option only, which is the correct answer. So clock feed through is caused by, among the following four options, which is the correct option? That's right. So as already explained, so capacitive coupling between the clock input of the precharge device and dynamic output node causes the clock feed through. Now, along these lines, we have one more question which says that charge leakages, charge sharing capacitive coupling, and clock feed through causes A. Signal integrity issues, power supply noise, high power consumption, and high area consumption. So, what is the correct answer to question number 2? Anyone? What is the correct answer? Option A. That's right. Option A is the correct answer. Now I have a just give me a second. Just give me a second. Yeah. So what do you mean by signal integrity issues? Anyone? What is meant by signal integrity issues? Can anyone tell me? If you want, you can unmute yourself and answer, or if you are comfortable in chat box, you can write. So what I'll suggest is you guys should look it up, although you knew the answer, but you should know what is really meant by signal integrity issues. Now question 3. In a multi-stage logic network, the power delay is dash when each stage bears the same stage effort. So what will be the power delay if each stage shares the same stage effort? Option A highest, option B doubled, option 3 least, option D 0. So what is the answer? Anyone? What is the answer to this question? if each stage bears the same stage effort, what will be the delay? Is it highest? Is it lowest? Is it zero or is it doubled? A, B, C, D. I think you have done these type of questions definitely in your lectures. So it will be option C, least. So when each stage bears the same path effort, so it will encounter the overall stage will encounter the least delay. Now I have a question. I have marked this question. I have marked only part A of it. So what I would like you guys to do is do only part A at your end right now. And once you are done, please let me know. Or if you are still doing, I'll give you 4 to 5 minutes to do it. I think 5 minutes is sufficient to do it, and then the other part I'll even show the part A, but I would like you guys to solve it first. So I'll read the question. It states that consider a 1 bit full adder where the sum S is given by A XOR B XOR C in, and the output carry C out defined as the majority function of the inputs where A, B and input carry is given by C out equal to AB plus BC plus AC. So majority function is basically when you have a odd input gate, so it gives output 1 if majority of the inputs are high. So here if there are 3 inputs, it will only give output 1 if any of the 2 inputs are, if at least 2 of the inputs are 1, not any of the, if at least 2 of the inputs are 1. So that's how it's written as AB plus BC plus AC. So this is a full adder. You must be knowing that. So S is given by A XOR B XOR C and C out is given by AB plus BC plus AC. Implement this function using a static CMOS gates and assume you have A, B, C and their complements available that are readily available. That means A bar is available, A is available, B is available, B bar is available, and so on. What I would like you guys to do is think about implementing it in one stage only. Since we have complement inputs available, do it in one go. As I told you last time also, there are multiple ways of doing the question, but I preferably deliberately picked up this question. I wanted to show you something in this regard. And fast transitor logic, you don't need to do that as of now. I'll show you that after we'll do this static CMOS gate. So you do the CMOS one. I'll give you 5 minutes and then I'll show the solution to this question. Has anyone done it? Anyone? So I'll just wait for one more minute because we have to show other questions as well. At least I hope you have attempted it. That's the least you can do at least. So now I'll be showing it. So what we have here is we have a sum block and a carry block. So let's just first implement the sum. So sum is given by A XOR B XOR C in, right? Can be written as A XOR B. We all know it's written as A bar B plus A B bar, and then this is XORed with C in. Now if you want to evaluate this part, what you can do is you can write A bar B plus A B bar whole bar C in plus A bar B plus A B bar C in bar. Everybody got this step? Can you please confirm? What I have done here is simply XOR with C in. You got it? Now what I'll do is A bar B plus A B bar. So XOR gates complement is simply XNOR gate. So it will be A B plus A bar B bar C in plus A bar B plus A B bar C in bar. Now writing the complete form A B C in plus A bar B bar C in plus A bar B C in bar plus A B bar C in bar. Right. So this is S. And what about S complement? S complement will be all those minterms that are not here. So that will be A bar B bar C in bar plus A bar B C plus A B bar C in plus A B C in bar, right? So this is your final expression for complement of sum. Now this part we can easily implement using a pull down network. I'll show you how. And since A, B, C, N and their complements are available, we don't need to worry about the complement part. So we have like this. This is A bar, this is B bar, and this is C in bar. This is A bar, this is B, this is C, this is A, this is B bar, this is C in, this is A, this is B, and this is C in bar. Now I'll implement pull-up network. So this is a part where I wanted your attention. So last time, as I also told you, there are multiple ways of doing it. I'm just showing the one of the ways. Just give me a second. Now what I can do is I can implement pull-up network exactly like this. This is A bar, B bar, C in bar. This is A bar, B, C. This is A, B bar, C in. And this is A, B, C in bar. And this right here is your S. So this is how you implement a sum block using static CMOS gate. Can you confirm the functionality at your end? Just check it whether it performs the correct functionality. And you can say that I have not made the pull up network dual of pull down network, right? They are not dual, but the functionality is being performed. It is a static CMOS gate. So if I wanted to do the what should I say, dual of pull down network, it will be different, right? Can you tell me why this design will be preferred over that? Just a question. So first of all, what will happen in the pull up network when I do the dual of pull down network? Whatever is in series will be in parallel, and whatever is in parallel will be in series, right? Is that clear? Can you confirm that? Now my question is, why this design where the pull up network and pull down network are exactly same will be preferred over that where I am making complement in this case? Why? Can you tell me? Even I am exploring that reason. I want to hear the reason I have in mind. I hope that's the correct reason. Any idea? Basically, pull down, I'm saying pull down will remain as it is, pull up will change. So, what will be the issue with that? If I make, there is no issue, but I am paying some penalty. What is that penalty? So, I think you guys are not got the idea of the sizing part. So, once I do the, yeah, larger bit, exactly. So, once I do the complement of that, I will have four transistors that will be going in series, and I have to make PMOS more wider as compared to this case, and I'm thus paying an area penalty. That's the that's the reason I thought. Maybe I hope that's the correct reason. And apart from that, now we have to implement the C out block. But before going to that, do I need to elaborate on something? Nah, I think we can move forward to the this part. Now we have C out. So C out is given by, and by the way, there is other way of implementing it. You can have multiple ways, so you just need to have one that will provide the minimum delay and minimum area. So I think among that, this one will probably give the minimum area and minimum delay. You can check at your end, and definitely there are other implementations as well that you can figure out. Now the C out part. So C out is basically your AB plus BC plus CA. So C is basically C in I. Just write C here. So and C out complement will then be equal to C out. You can write like this: AB plus you will take C common and it will be B plus A, and then C out bar will be equal to AB plus C times B plus A whole bar, and this that is equal to A bar plus B bar using De Morgan's law dot C bar plus A bar B bar. This is just the De Morgan's law. So C out bar is given by this, and this is very easy to implement using a CMOS gate. I'll show how. So you have this VDD, you have VDD. Let's first make pull down network. So we have A bar plus B bar, so it will be in parallel, right? A bar plus B bar, and then C bar is in parallel with A bar plus B bar, so it will be something like this. A bar, this will be B bar, and this is ground. This is C bar. Now pull up network. So here is C out. Pull up network will be like this. Whatever is in series will go in parallel, and whatever is in parallel will go into series. So A bar B bar, and then right here you have C in parallel with A bar B. Now it will be in series. C in will be in series with parallel combination of B bar and A bar. This is C out, right? So this is how you implement C out. There is another way of implementing C out as well. So C out is given by AB plus BC plus CA. If you take complement, it's complement directly, it will be A bar plus B bar times B bar plus C bar times C bar plus A bar. You can implement this thing directly like this: A bar B bar. Now it's in series with C bar B bar, and this thing is in series with C bar A bar. So this is your pull down network, and this is your C out, and your pull up network will be somewhat like this: A bar B bar, B bar C bar, C bar A bar. Is it clear? Any doubts? Now we have only solved part A of the question. Part B asks us to, so this is question 4. So what is pass B? Pass transistor logic. So have you guys studied about pass transistor logic? I think you have, right? So let's implement it using pass transistor logic. Let's first implement the sum block. So it will be like this. So take a look here. A bar B, A B bar, and this will be A B, A bar B bar. This will be C in bar, this will be C in, and this right here will be your S. So can you tell me what does this block do and this block, what are they doing? What function they are performing? Correct. Correct. XOR and XNOR, and ultimately it goes to another XOR. Now we have to implement. We have to now implement. What should I say? We have to implement now the carry block. See out. So carry block can be implemented like this. Now question to you guys. What should be here? At the question mark, what should be it? I think VDD is already there, right? VDD is already there for A and B. If not VDD, then what? I think that should be pretty obvious. If not VDD, then what should be there? So you can easily evaluate. Now let me just give you a hint. So this is A bar and B bar. So when A and B are 0, this will turn on and my Cout is 0. So what should be here? No. If my A and B is 0, what is my output of Cout? If A and B are 0, what is the output? If A and B is 0, will it depend on C? My output will depend on C? No. No matter what my output is, it will be 0. So here it is ground. And do you know why it's PTL implementation is like this? I often see people doing it using sorry, 6 transistors and doing AB plus BC or CE. So why VDD and 0 are put here? Do think about this implementation. Take a look about this implementation, why it was made like this. So what I would like you guys to do as a part of your home exercise, first ignore this implementation and try to make a implementation out of your own self, and then evaluate and why we went with this implementation. Is this clear? Now I have this question which reads as, the logic chain in the following figure is constructed with r equal to 2.5. First of all, I think you might not be aware of this r factor. So do you know what this r means? I think it's not there in your lecture notes, so I'll clear that. So do you know what r is? Here what r signifies? Anyone? Does anyone know what this r means? So I'll tell you what this R is. Well, first let me read this question. So the logic chain in the following figure is constructed with R equal to 2.5. Determine the output optimal input impedance for each stage to achieve the minimum delay through the red colored path using logical effort method. You need to find C1 by C and C2 by C. So first of all, I have this reference inverter, and this PMOS is sized as R, and this is 1. This is V out, V in, and this is V out. So what is the logical effort of a two input NAND gate? Anyone? Does anyone know what is the logical effort of two input NAND gate? 4 by 3 exactly. But it's 4 by 3 only when you take a inverter of 2 is to 1 and R is 2. Typically, actually I have taken this from my lecture notes, and the professor used to shape up the questions like this. Usually the PMOS inverter is made like 1 is to 2. So that is the reference inverter, but it can be 1 is to R as well. So when R is equal to 2, your G for NAND is simply 4 by 3. But if R is some variable R, so then your NAND is equal to 1 n plus R by 1 plus R, where n is your number of inputs and R is the reference size of the PMOS. So just put R equal to 2 and n equal to 2, you'll get 4 by 3, right? Similarly for G NOR, it is 1 plus NR by 1 plus R, where n signifies your number of inputs. So if for a two input NOR gate, n is equal to 2, and if we take reference inverter equal to 2, which usually is 2. So just for the question here I have taken R equal to 2.5 because I had taken it from my lecture notes. You just remember for now R is most of times 2. So then R equal to 2, it will be 5 by 3, right? Which you guys are well aware of. Now we need to figure out. So don't worry about this R and all. You can assume R equal to 2. If it's not given, it's always equal to 2. So now what we'll do is we'll have to find the optimal minimum delay size, and we have to size it accordingly. So this can be done by first finding the path effort, which is given by F, and that is equal to, what is F equal to? Can anyone tell me what is F equal to? GBH, correct. GBH. G is your path logical effort, B is your path branch effort, and H is your electrical effort. G is equal to, so we have to take red path only, right? So G is equal to G NOR times G NAND. When I write this 2, you know what I mean here? What it means, the number of inputs, and then G NOR again. So I'll go by my definition of NOR. So it will be n is equal to 2, it will be R n equal to 2, 1 plus 2R by 1 plus R when n equal to 2, and this will equal to G NAND will be equal to 2 plus R by R plus 1. If you put R equal to 2, that's your value, 4 by 3 and 5 by 3, right? So it will be 1 plus 2R by 1 plus R multiplied by 2 plus R by R plus 1 multiplied by G NOR is again 1 plus 2R by R plus 1. Now plug the values. So you will get, it will be just cross check at your end, 6 by 3.5, 4.5 by 3.5, and 6 by 3.5. Now branch effort is B equal to B1 times B2 times B3, but how many branches are here? Can anyone tell me how many branches are here? 2 and 1. Are you sure there are 2 branches? How many branches are there? Just consider the red path and see how many branches are there. Number of branches, how many number of branches are there? Other than that, I don't see any branch. There is only one branch, right? And you know that branch effort B1 Bi is equal to C on path plus C off path divided by C on path. And for B1 it is equal to, so on plus off path is taking this 2 input NAND gate and 3 input NAND gate. So if I go by formula, it will be 3 plus R plus 2 plus R, and 2 plus R is your on path. If R is equal to 2, it simply is 5 plus what should I say, 5 plus 4 simply. Then it will be equal to 5 plus 2R by 2 plus R, and which is ultimately equal to 10 by 4.5. Electrical effort is given by, what is electrical effort here? H, capital H. What is capital H equal to? Yes, it is 10. It is basically C out by C, so that is 10. Now my F is equal to G, B, H equal to, G is 6 by 3.5 multiplied by 4.5 by 3.5 multiplied by 6 by 3.5 multiplied by branch effort is 2.22. If you do the maths for this, it comes out to be 2.22, and then it is multiplied by 10. No, I think 10 by 4.5. 2.22 is something different. Let me just check my numbers. 6 by 5, 3.5, 2.5, 10 by 4.5. How much is 10 by 4.5? Yeah, it's only this. And it comes out to be, F comes out to be, don't worry about the calculation part of it. You can always check at your end. Just look at the concept part. Now, just give me a second. I'll just check the condition. Ten divided by 4.5. Yeah, it's correct. So it comes out to be 83.96, and my F optimal. So F optimal. How is F optimal given by? So anyone? What is F optimal given by? What is F optimal given by? Yes, exactly. So it is given by F raised to power 1 by N. So it is 83.96 raised to power. What is N here? Anyone? Let me show you the circuit. What is N? How many stages are there in the red path? Correct. So it is 1 by 3, and it comes out to be 4.3789. So this is, now we have to find the this individual capacitances. So my state effort is state effort is optimal state effort is 4.3789. So F is equal to G3 H3, right? So it is equal to 6 by 3.5 multiplied by 10 C by C2, basically this by this, and this is equal to 4.3789. This number we got, that implies C2 is equal to 3.95 C. So C2 by C we got. Now we need C1 by C. So G2H2 is equal to F optimal. So it is 4.5 by 3.5 multiplied by 3.915 divided by C1 and 3.95 C basically. So ultimately C1 comes out to be 1.15C. I'm skipping some steps which are simply basic mathematics steps, which I hope you can always check at your end. Now we got C1 by C and we got C2 by C. Now there is one more step. Now since you got these values, you can always check your calculations. So you know that you can always check your calculations whether you have done right or wrong. So this is called check step. So what you will do is you will take this first one here. So that effort at that point the effort is G1 H1 B1, right? Because there is branch that is equal to F optimal. That implies 6 by 3.5 multiplied by 1.15 C by C in, right? Which is equal to C itself, right? Is equal to 2.2. And if you do the calculation, ultimately C in comes out to be close to C, which validates your point. Got it? If you do the maths, 6 multiplied by 1.15 multiplied by 2.4 divided by 3.5, it comes out to be equal to C. No, no, this is equal to, should I say 4.3789, obviously. And once you do the calculations, C in comes out to be C, which validates your calculation, right? Got it? Now, I have a question that is basically that we did last time based on the NORA logic, or should I say NP logic. Some of the students were having basically difficulty, so that time I asked you to practice. I hope you have practiced, and for that I have given you this question. So it is the question states that implement the following function f using NORA logic along with a high impedance latch as discussed in class. So high impedance latch is simply like this. This is clock bar, this is clock, and your f is taken to be here. So basically the input you have to implement up to here. So whatever logic you have to implement, you have to implement up to here, and this should be basically your f bar, and this will be your f ultimately because it's an inverter. So implement the following function using NORA logic along with the high impedance latch discussed in the last class. Given input and its complements are readily available, and you have to make sure transition count is minimum. So implement this. I'll just give you 3-4 minutes and then I'll show the solution. I hope you have done it. If not, I hope you have done it. If not, now let me just show the solution. So f is given, f bar is given here. So f bar is given, that implies f will be simply equal to ab plus bc, a bar plus b bar plus c bar, d bar, e bar, f bar. It's complement, right? So now first stage that needs to be implemented using the NMOS logic. So pull down network basically. What we'll have here is we'll have clock. Then this part we can easily implement. This is a plus b plus c. So it will be like a, b, and c. And then here what we will do is we'll have a bar, b bar, and we will have c bar. And then we will have clock here also, and this is ground. Now this is basically the output I'm taking here is basically a plus b plus c, then a bar plus b bar plus c bar, its complement, right? Now this will go input to the PMOS logic, P block, and since we needed to apply complemented, it's complemented itself. So this is right here, this part, and then I'll have D bar, then I'll have E bar, and then I'll have F bar, and here it will be clock bar, here it will also be clock. Now output, where will I take the output? I'll take here and feed it here. So here what it is, this is simply your a plus b plus c, a bar plus b bar plus c bar dot d bar e bar f bar. Basically it's complement. So if I have to write here, this is basically your f bar and this is your f. Any doubts in here? So this was because last time some people had doubts related to Nora logic, and I told them to practice. I hope this time it's clear. And this one is a slightly easier example as compared to the last time. Now, if there are not any doubts, let's just move forward to question number 7. Basically, question number 7 has two parts. Question 8 is just the continuation of question number 7. So I can just write it here. Question 7, part B. So the circuit that is given below implements the logic path shown by a dotted line, right? It goes from this, then to A, to then this, and there is some S block in between. And it is implemented using NOR gates as shown, and S block implements logic function that is given here. So it implements this function. Now we have to implement logic block S so that the path effort GBH from I1 to O1 is minimum. Note in S we can only use two input NAND gates or NOT gates. So we have to first implement this S block, and then we have a part B that we'll discuss later. And the S block we need to implement using NAND gate or NOR gate, two input NAND gate or NOR gate, NOT gate, sorry, and it should be minimum. Now S is given by A plus BC plus D whole bar. S bar is simply equal to, or should I say S is simply equal to A plus BC plus D bar, bar, and bar. Right, I hope you got this point. And that is equal to A bar dot BC plus D bar, and then this bar. Now we have to implement this function. What we will do is we will apply this is B, this is C. Remember, we have to only use NAND and NOT gate. And this is D. So this is BC bar and this is D bar. Now this will go to another NAND gate. So what will be this output? It will be BC bar dot D bar whole bar, that is BC plus D, that is simply equal to BC plus D. Now what I will do is I'll just take another NOT gate, and this is BC plus D bar, and here I'll take A and its complement, so it is A bar, and feed it to NAND gate, so it is A bar. So this is A bar dot BC plus D bar and whole bar. Now check this. I have to implement this thing. What is missing? I'll show you that. I'm coming that to that step. Exactly, I'm coming to that step. And then you will have a NOT gate, and this is your S. Now you know why I had to, just for the visualization purpose. Now you know I have put two complements there, because here I got complement and another complement, and I implemented the function. So this is the S block that is to be implemented using two input NAND gates and a NOT gate. Now we have to look at this path. We'll see what the next part asks us to do. So the next part asks us to, for the implementation in A. So A is basically this part, question 7A. So I'll just write it here. So for the implementation in A, compute the minimum delay throughout the path I1 to O1. You can assume the parasitic delay in D, basically GH plus P formula. Inverter is 1, and for NAND 2 and NOR 2 are, it's 2 units. We don't need to calculate the input capacitance, and given the gates are equal to 2. So R I have already elaborated. R equal to 2 is your default, right? Where you will get the logical effort for NAND as 4 by 3 and for NOR as 5 by 3. Basically the size of PMOS is R equal to 2. Now we need to implement the, find the, what should I say, through the path I1 to O1 we need to find the delay, minimum delay. So what I will have here is, we'll first have this thing, NOR gate, then I'll have a NOT gate, then I'll have a NAND gate, and then I'll again have a NOT gate, and then I'll have a NOR gate. Basically this, and then I have to follow the path of A, not NAND, not NAND, not, and then I have my output, which is 10C, right? So G here will be 5 by 3, since R equal to 2, G will be equal to 1, G will be equal to 4 by 3, G will be equal to 1, and G will be equal to 5 by 3. So F is equal to G1, sorry, F is GBH, that I know. I should rather say G is equal to G1, G2, G3, G4, G5, G1 times G2 times G3 times G4 times G5, right? And there is no branch, and H is equal to 10 C by C, that is equal to 10. My F will be equal to G B H, so it will be equal to G1 times G2 times G3 times G4 times G5 multiplied by 10. So it will be equal to 5 by 3 multiplied by 1 multiplied by 4 by 3 multiplied by 1 multiplied by 5 by 3 multiplied by 10. So it is equal to 370.37. And then my optimal delay, what should I say? My delay D is equal to NF1 N plus P. So it is equal to, D is equal to, N is 5, right? 1 2 1 2 3 4 5 multiplied by 373.7 raised to power 1 by 5 plus P is equal to your 2 plus 1, 2 plus 1 1 1 2 plus 1 That's 2 plus 1 plus 2. So your D is equal to 24.32 units. Any doubts? If not, then we can move forward to the last question of today's live session, and I would like you guys to solve that first, then I'll show the solution. So this is the question. So refer to the circuit shown in the figure that is given to you, and you need to find C1 and C2 in terms of C, exactly what we did in this question. Uh, Let me show. Does anyone want to speak? Your voice is breaking through. If you are asking any question, your voice is breaking through. Kindly use chat box. I'm not able to hear you properly. So this question, you need to follow exactly not exactly the same methodology or same concept that you have done for this question, right? So find C1 and C2 in terms of C so that delay between A and B is minimum using logical effort, and R is equal to 2.5. So path is like this, right? So you need to follow the same methodology and determine the delay from A to B given parasitic delay of inverter is P inverter, and that P in NAND 2 is equal to twice the P inverter. Just do part A, part B, we'll do it together. So just do part B and then I'll show the solution. I'll just give you 5 minutes and I think that should be sufficient for this question. So, has anyone solved? If not the complete solution, at least if what is the path logical effort? So, what is F? The path total path effort. E1 is equal to 12.39 C. We have to check. What about C2? Okay, let's just go a couple of steps back. What is path effort? F, capital F, and that you have calculated. What is that equal to? Has anyone calculated that? F, that is equal to GBH. And remember, R is equal to 2.5. Have you taken R equal to 2.5 or R equal to 2? Okay, so what was the value of F? I think there is some maybe calculation mistake. Let me show. So before we proceed, let's just write what we have to calculate. F is equal to GBH, and my G is equal to path logical effort, which will be equal to G NAND of 2 times G NAND of 2, basically this path. Then again G NAND of 2, and then G naught. So G NAND of 2. So basically, if R was 2, it will simply be 4 by 3. But there is a generalized formula that is equal to 1 plus, oh sorry, 2 plus R divided by 1 plus R. This is also 2 plus R divided by 1 plus R, and this again is 2 plus R divided by 1 plus R, and ultimately it's 1. And this is equal to 4.5 divided by 3.5, 4.5 divided by 3.5, then 4.5 divided by 3.5 multiplied by 1, and this is equal to 2.125. Just cross check these values. So G is equal to 2.125. Now we have to find path branch effort, that is B, that is equal to B1 times B2. So here it is B1. So B1 is basically C, this is C on path, this is C off path. So C on path is 2 plus R, C off path is 1 plus 2R, right? Divided by 2 plus R. So this is 3 plus 3R divided by 2 plus R, that is equal to 2.33. R is equal to 2.5. Don't forget this. And now B2. So now my branch B2 is here. B2 is equal to, my on path is this, so it is 2 plus R. Off path is this, 2 plus R. This is also off path, so this is 1 plus 3R, right? Why I've taken 1 plus 3R here? Why 3? Anyone? Yes, 3 input, exactly. 1 plus 3R divided by 2 plus R. You know that how this formula comes out, 1 plus 3R for NOR gate. So basically it's 1 plus NR for NOR gate and N plus R for not NAND gate. So if it's a 2 input NAND gate, it will be 2 plus R. If it's a 2 input NOR gate, it will be 1 plus 2R, right? And once you do the maths, it comes out to be 5 plus 5R by 2 plus R, and it comes out to be 17.5 divided by 4.5 and 3.889. Yeah, I'll tell you. So what is B equal to? Bi, right? Bi is equal to your C on path plus C off path divided by C on path. This much is clear, right? Now my on path is this thing. So NAND is my on path. So for NAND, it is 2 plus R. Basically, if R is equal to 2, it's 4, and for NOR, and for NOR, it's 1 plus NR. So for 2 input NOR gate, it will be 1 plus 2R. That's what I have written here. 1 plus 2R divided by C on 2 plus R. So if your R was 2, your NAND branch of effort of NAND gate would have been 4R plus 4 plus 5 divided by 4. 4 from NAND, 5 from NOR, and divided by 4 from NAND. But since R is equal to 2.5, that's why we have to keep it in terms of R and then plug the value of R. Got it? You know why it's 1 plus NR for NOR gate? Or let's just say ignore n for a moment and ignore r equal to 2.5 for a moment. So for 2 input NOR gate, why is it what should I say 5, and for 3 input it's 7? For, you know how these capacitances come out? Basically these are your input capacitances, right? And your input is going to the pull up network and the pull down network. In case of a NOR pull down network, for a 2 input NOR will give 1C, 1C, yeah, and the pull-up network will give 4C. So it is 4 plus 1, 5C. I hope you got it. So now we got B2 as well. So now what remains is the final calculation. So B is equal to B1 times B2, that is equal to, so what was B1? B1 was 2.33 and 3.889 was B2. So it is 2.30 multiplied by 2, 3.889. Yes, so it is equal to 9.073. F is equal to GBH. So G was 2.1253, B was 9.073, and H, let's just write H here. How much is H? Anyone? Yes, H is 10. 10C by C, that is 10. So multiplied by 10 and it comes out to be 192.8285. And F optimal will be equal to F raised power 1 by N. What is N? Tell me. Exactly. So it is 192.8285, 1 by 4, and that is equal to 3.7265. Now consider this part. So G naught H naught should be equal to F optimal. That implies H naught is equal to, basically it will be equal to 3.7265 will be equal to 10C by C3, because for a naught, G naught is equal to 1. That implies C3 is equal to 10 by 37265, that is 2.6825 C. Now consider now consider this one. So G NAND 2 H NAND 2 is equal to F optimal, that is equal to 1.2857 multiplied by 2.6825 C divided by C2 is equal to 3.7265. This is F optimal. That implies C2 is equal to 0.92. I'm just skipping calculation part. You can always check them. See, now we are at this point. So G NAND 2 multiplied by H NAND 2, and also I have branch 2, this branch. B2 is equal to F optimal. That implies 1.2857 multiplied by 0.9258 C divided by C1 multiplied by 3.889 is equal to 3.7265. That implies C1 is equal to 1.2412 C. Now we have one more step, that is check step. So we can always check it. So for check we have this thing, G G NAND 2 H NAND 2 multiplied by B1 is equal to F optimal. That implies 1.2857 multiplied by 1.2422 C, that is basically C2, divided by C in multiplied by B1, that is 2.33, is equal to 3.7265. That implies C input is equal to 1.2857 multiplied by 1.2422 multiplied by 2.33 divided by 3.7265, implies C input is approximately equal to 0.9967, that is almost equal to C in is approximately equal to C, which validates our calculations. and the part B, this thing. So your D is simply equal to n f optimal plus summation of parasitics. N is 4 multiplied by 3.7265 plus sum of parasitics is basically twice NAND and twice NOT. So that is equal to 3 into 2P inverter plus P inverter. Basically 3 NAND gates, 1, 2, 3 and 1 NOT gate. And NAND gates inverter delays twice, and that is 14.906 plus 7 times parasitic delay of inverter. This is how you have to do this question. So if there are any doubts, please let me know. Yeah, sure. So first of all, has the due date been passed for the assignment? So, see, I have time and again said this. So, whenever there is an assignment, if there is a problem pertaining to question, the question is wrong or the question has multiple answers, please update the NPTEL team and ask them. If the due date is passed and you have some doubt, I'm very much welcome and I'll definitely help you. But if the due date is not passed, I can't really help with the question unless the question is wrong. Please ask the what should I say, the concerned team. You can always raise the question in the forum. Actually, I'm not allowed to discuss the uh, basically problem solving sessions are intended to help you in the assignment related problems, but I can't directly help you in the problems. If there is some doubt or if the question is incorrect, please ask them. And if there still is a doubt after due date, then I can definitely help you that time. Yeah, anything else? If there are no doubts, no further queries related to this week's assignment, I'll just close the recording first.